It's my pleasure to introduce Dean D'Souza. Dean D'Souza is a lecturer in developmental psychology at the School of Health and Psychological Sciences, Department of Psychology, University of London. He is the principal investigation founder in 2017, very recent, of the Erlang Lab, which is the Early Learning and Neurodevelopment Lab, which also includes Dr. Hannah Souza as a co-PI. He got his master's degree in cognitive neuroscience in 2010 and his PhD in psychology in 2014, both at the University of London. Among other positions, he was a research associate at University College London, a senior lecturer in psychology in Anglia Ruskin University, and a research visitor at the University of Cambridge. Dr. Dean D'Souza and collaborators study typical and atypical neurocognitive development, in particular the growth of early language and cognitive abilities in typically and atypically developing populations, looking at factors such as visual attention, multimodal integration, parent-child interaction. Among the exciting lines of research he pursues are the following: early predictors of later developmental outcomes in Down syndrome, Fragile X syndrome, and Williams syndrome, the effect of exposure to a bilingual environment on cognitive development in infants, the relationship between sleep and language development. Today he's going to talk about neurocognitive constraints on early language development. Please join me in giving a warm welcome to Dr. Dean D'Souza. Thank you.
Yeah. Okay, thank you for inviting me. I'm actually just glad I got up here because I hurt my foot. So I've been moving very slowly, and especially up and down stairs, but I'm up here now, so that's good. Okay, so today I just want to talk about neurocognitive constraints on early language development. Taking a look at the website of NeuroD-WELL, the main focus of NeuroD-WELL is in early development of language in neurodevelopmental disorders or at risk of developing language delay. And this is important because little is known about these disorders early in life. And the reason why I'm highlighting this is because I really like this phrase, early emerging abilities and their development, because I think sometimes we often lose track of development in amongst all the data. So, for example, when we think of neurodevelopmental disorders, which by definition is atypical development of the central nervous system, we often think of neurodevelopmental disorders as being a range of conditions, each with its own distinct profile of relative strengths and weaknesses, which is true, but only really in in older children and adults. So, for example, with Down syndrome, you'd be able to characterize Down syndrome as an individual with poor motor skills, mild to moderate cognitive impairments in working memory and other types of memory, short and long-term memory, delayed language, avoidance strategies. They are keen to socialize. Weak muscle tone is a very distinctive feature of Down syndrome. And then if you look at Fragile X syndrome, you see some commonalities, but also some differences. So commonalities would be also mild to severe, sometimes cognitive impairments in working memory, delayed language, but also things such as avoidance of social interaction, impaired social interaction skills, and of course social anxiety. And of course we know that a lot of children with Fragile X syndrome go on to develop autism, as do a lot of children with other neurodevelopmental disorders. And then Williams syndrome, again, a very different profile. Some things are very common, so again, delayed motor abilities, delayed mild to moderate cognitive abilities. Very distinctive feature, if you're not familiar with Williams syndrome, is their visuospatial construction ability. So if you just get them to draw something very simple, they find it really, really difficult. Or if you ask them to copy something, they find that even more difficult. So representing the visual world, they just find really, really hard. So you have these distinct profiles, at least in older children and in adults. And what these neurodevelopmental disorders mean, or these profiles mean, is that each population, or the assumption is that each population will share a set of common features. So Carolyn Mervis says this about Williams syndrome, that a relatively consistent pattern of cognitive strengths and weaknesses, which is likely to hold independent of IQ, has emerged. So she identifies these common traits that she assigns to this Williams syndrome cognitive profile. And she also goes on, we also assume that these profiles are relatively stable. So Carolyn Mervis says the Williams syndrome cognitive profile does not vary greatly with chronological age or overall level of cognitive ability for individuals. So basically these features are quite stable over time, relatively stable over time. And finally, we assume that a profile is fairly unique. So it's not something you will see in the general population, or at least if it is, it will be very rare that you'll see someone with this profile. So these are assumptions that we have about neurodevelopmental profiles. And we know that they exist because we can identify children based on their behaviour as well as their features, their physical features. But very little is known about how this profile emerges and develops over time, and that's why I think workshops like this is so key. So as a first step to taking a look at this problem, this gap in our knowledge, what we wanted to do is we just wanted to look at a range of young children, so between 8 and 48 months of age, and we looked at these children, they were infants and toddlers with Down syndrome or Fragile X syndrome or Williams syndrome, and we just wanted to look to see what does the rough profile look like in these children. So we tested them on the Mullen scales of early learning, which measures motor ability, language abilities, or at least communicative abilities, and something called visual reception. If you're not familiar with the Mullen scales of early learning, visual reception basically measures, what is it? I can't see it. It measures visual perceptual ability, spatial awareness, and visual memory, and these kinds of things. So you can think of it as kind of a visual IQ, if you like, or perceptual. Okay, so we measured these in these children, and I'm just going to show you the results of what we found. And so what we're looking for is for very distinct profiles in these young children. With Down syndrome, this is what we saw in Down syndrome, so very little difference between the domains in Down syndrome, but overall it's increasing over developmental time, as you would expect, but very little difference between these 5 domains. So which is fine motor, gross motor, receptive language, expressive language, and visual reception. If we look at Williams syndrome, we see a similar pattern. No differences between these domains. You might expect beforehand that with Williams syndrome they're supposed to be very good at language, or relatively good at language, so you might expect this to start early, but actually if you just compare the domains early in life, you see no differences between these domains. And then Fragile X syndrome, there's fewer of these children, so it's a little bit more noisy, but you kind of see a very similar pattern. Just to show you, just to put in, that black line is what you'd expect a typically developing child to do. So that's someone who's developing typically, so along the chronological age they will have the age equivalents and I'll just add the black lines. So those black lines are what you'd expect a typically typically developing child, how they would roughly progress, and you can see the children with these disorders, how they look. So it's interesting because you can't really tease apart these domains in these children. There are some interesting features. So for example, it looks as if, roughly speaking, there's an increase in ability. So the y-axis is age equivalent score, so this is how much we'd expect them where they should be. And you can see a little increase until around 23 months of age, where it seems to plateau a little bit. And you see this in all three groups. So it'll be interesting to see whether this is a key feature in a larger population. You also see, maybe with Williams syndrome, you can see a bit more variability as they're getting older than you do with Down syndrome. So that's a kind of an interesting feature that you can observe. And possibly with Fragile X syndrome, you might be able to see that their expressive language score is relatively low, perhaps from a very early age. If we can clear up all of these confidence intervals and we can just look at that in a little bit more clearly, you can see that expressive language, which are the green dots, start off very low, and they kind of remain low over chronological age. And that black line there is what you'd expect for typically developing child. And so this is the kind of gap. So you can see a typically developing child, and you can see that actually over time expressive language is relatively flat in this group. Okay, so that's very interesting. But now let's look at if you compare the disorders all together. So this is gross motor ability. And you might expect maybe differences between Down syndrome and the other groups. But actually the children with Down syndrome and Williams syndrome, they're performing very, very similarly at this age. So the lines are almost on top of each other. Like I said as well, with Fragile X syndrome, it's a smaller group, so it might be a little bit more noisy. And then this is fine motor ability, and again you see a similar pattern, so almost no differences over time between the Down syndrome and Williams syndrome. And the black lines are typically developing children. And then you see visual reception, and again you see the Down syndrome group and the Williams syndrome group are performing almost exactly the same. So you see no differences at this age between them on this particular measure. Okay, looking at receptive language. So this is again where you might expect there to be large differences, especially with Williams syndrome. But again, you see no differences between Williams syndrome and Down syndrome. And no differences as well in expressive language between the two. So again, the lines are virtually on top of each other. So this is quite interesting, because what it suggests is that these profiles emerged over developmental time. Okay, so if we look at their non-verbal IQ, again what we see is that there are no differences between Down syndrome and Williams syndrome, and again with verbal IQ, you see none. So this is really interesting, because again you'd expect there to be differences, and this is mental age. So this is the score combined, but without the motor ability. Okay, so again, we need a larger sample, especially for Fragile X syndrome. But what we can see is that performance perhaps becomes more variable over developmental time. Initially, you might think that this is an artifact of the design, but there are different patterns, including greater variability in Williams syndrome. Even though there's very little difference in mean age equivalent between Down syndrome and Williams syndrome across development. You also see some possible differences between Down syndrome and Williams syndrome and Fragile X syndrome. In particular, expressive language seems to be very poor across development in Fragile X syndrome from a very early age. Normally, children with Fragile X syndrome are diagnosed a lot later, so there's not many studies that go this early back. So what we see is that performance is not just delayed, which is what we'd expect, but it might become worse over time. So if it were just simply delayed, we would expect a pattern like this. So same kind of development, but happening later in time. But that's not what we're seeing. What we're seeing is something more like this, which is differences not just in delay, but also in the rate of development, and a lot of variability, and this variability seems to increase over time. So this suggests that individual differences increase over time. And how can we explain that? And I think this is the great challenge that we have as developmental psychologists and practitioners and so on. So I'm sure we would all agree that development involves the interaction of many diverse, interconnected and interdependent factors. And development is also about how the child is adapting to all of these constraints. And these constraints might be internal, such as genetics, so in Down syndrome it's trisomy 21, and these can be external. So for example, this could be how you're raised in an environment. And all these factors, I'm hoping we all kind of already know this, all these factors interact with each other. So for example, genes just don't operate in isolation. When I was a student, I assumed that in Down syndrome that could be explained by a 1.5 increase in the genetic activity on chromosome 21. But we actually know that some genes on chromosome 21 are overexpressed, some are underexpressed, some genes on other chromosomes are overexpressed, some are underexpressed, and it's simply because there's all these interactions that are happening. And so it's not a simple story that everything is happening on this particular chromosome, because this chromosome is not working in isolation, but it's working in a context. And that context is the brain and the body, but also you've got to think about affect and cognition. Behavior is going to change how genes are expressed, and obviously how that's going to change the social and physical environment. So all of these things are interconnected. And they're also all interconnected, and you've got to understand how they interact over developmental time. And it's obviously a very complex story, which makes our job really, really difficult. I have tried to fill in some of these. So, for example, we found that genetic variation leads to variation in how we perceive and process patterns, including faces. We found that children with genetic syndromes have difficulty integrating multi-sensory information. They have difficulty with sleep, they have difficulty with attention, all of which are important for learning, of course, such as learning for language. We found that the languages we hear in our environment affect how we interact with the world around us, and also how, I can't see that. And also that this lasts, may persist into adulthood. And my master's student was studying how children with different genetic syndromes and cognitive profiles interact with their parents. My lab is looking at interactions between children with genetic disorders and their physical environment. PhD student is looking at emotion, and so on and so forth. So all these things we're doing but in isolation, but we need to somehow link them all together. So for one study I'm going to show you now, very as quick as I can show a large study, is early predictors of language outcomes in these children. So what we did was we tested children with Down syndrome, Fragile X syndrome and Williams syndrome. And we tested them at 8 months, 15 months, 36 months, and we're testing them now at 9 years of age. And we ran a really large battery of tasks, measuring various neurophysiological responses, cognitive processes using eye tracking, and a lot of other measures, including sleep, fine motor, and so on. I'm just going to focus on 3. So from cognition, I'm going to focus on visual attention. Neural response, I'm just going to focus on speech processing, and I'm also going to focus on sleep. So, we measured all of these in the same children. So with the visual attention, what we did was we used something called the gap overlap task. Some of you might be familiar with this. It's based on a very old task. And essentially what would happen is we would show infants a central fixation stimulus. As soon as the infant is looking at the central fixation stimulus, a target would appear on one side of the screen, and then we would measure how fast it took that infant to disengage their attention from the central fixation stimulus and to shift it over to the peripheral target. In the overlap condition, the central fixation stimulus would stay on screen, and then the peripheral target would appear, but the central fixation stimulus would remain on screen. So, in the baseline condition, what we're measuring is how long it takes the child simply to shift from the center of the screen to the target. In the overlap condition, because the central fixation stimulus is still there when the target appears, we're measuring how long it takes the child to disengage their attention from that central fixation stimulus in order to shift it and engage with the peripheral target. And what this helps us to do is we could subtract the baseline reaction times from the overlap reaction times, and that will give us a pure measure of how long it took that child to disengage their visual attention from the central fixation stimulus. Is that okay, clear? Yep, great. So what we have is a measure of how long it takes them to disengage their attention in order to shift it. So let's have a look at the results. So what we found was that children with Down syndrome were much slower at disengaging their attention in order to shift it to a peripheral target. And what we found was that this was related to language. So in all groups, typically developing Down syndrome, Fragile X syndrome, Williams syndrome, what we found was that if you're slower, so we split the group into relatively fast and relatively slow based on a simple median split. And if you're in the fast group, so you're faster at disengaging relative to your peers in your group, you had a better language ability than those who were slower at disengaging. And some of these differences are quite large, as you can see. So what you're seeing is a relationship there between visual attention and language. In speech processing now, we move to speech processing. Before a child can learn language, they of course have to learn to discriminate speech sounds, prioritize certain sounds in the environment. And this is delayed in neurodevelopmental disorders. So we wanted to look at whether there are atypicalities in processing speech sounds. So what we did was we were using EEG for this, and we were just interested in the social orienting response. So in the background, the child would just be watching a cartoon or something very simple. And in the background, so the child would be a bit oblivious to this, but in the background you would hear something like over and over again, and sometimes it would change in the speech sound. So it would go and then back to and sometimes it would change in pitch. So just go higher up in pitch. And what we're interested in for this particular talk is the social orienting response. So what happens in the brain when there's a change in these speech sounds? And okay, so for those of you who aren't familiar with EEG, what happens early on in the EEG waveform tells you something about how the brain is registering what's happening in the environment. And then what happens later on tells you something about how the brain is evaluating or processing what it's registering in the environment. And that's what we're kind of looking at. Is the brain attaching importance to the change in these speech sounds? So I'm just going to show you what these waveforms look like. So in typically developing children, what you can see if we just focus on the red line, so the black line is when it's just hearing the normal sounds, and then the red line is when there's a change in the speech sound. And just ignore the green line for now. So what we see this P3A in typically developing children. All you're seeing is that there's a difference between the two lines. That's exactly what you'd expect. I'll skip over that. In Fragile X syndrome, you see something very strange happening. I can comment on that later if you like. In Down syndrome, you see a really large P3A, and in Williams syndrome, you see a huge P3A, and this kind of matches what you'd expect because children with Williams syndrome are very sensitive and really hypersocial, and so you would expect that their brain on some level attaches a lot of importance to a change in speech sounds. So this is what we found, but the thing for this talk that I wanted to emphasize was that what we did was, again, for each group, we split each group into two. Those with by median split, those with a large P3A and those with a small P3A. And we just wanted to see whether this relates to language or not. And what we found is that there is a general effect of P3A on language, but particularly and especially in Fragile X syndrome. So in Fragile X syndrome, if you were in the high P3A group, you had a language comprehension age equivalent score of 20 months. So you were kind of behaving at the 20-month age child. Whereas if you were in a low P3A group, it was as low as 8 months. So there's a huge difference in the children with Fragile X syndrome. Okay, so moving on to sleep. On sleep, what we did was we just gave parents a sleep diary because we just wanted to give them something very simple and easy to do. In the past, we've used questionnaires, but it's very difficult to evaluate the validity of a questionnaire because obviously you can imagine it's quite hard as a parent to remember exactly what time your child went to bed and how often they woke up. So we no longer use questionnaires, so we just use this sleep diary, which is a much easier thing to do, and all that happens is the parents just simply draw a line whenever the child is asleep. So it's just very quick and easy to do. They do that over 7 or 10 days depending on the study. So we looked at, again, typically developing children, Down syndrome, Fragile X syndrome, Williams syndrome, and they were all about 30 months of age. And I'm just going to show you the descriptive data at first. So this is a 9-month-old typically developing child, and along the x-axis, what you can see is this is the number of days. So this is the days in the week, so 1 to 7. And this is on the y-axis, these, let me have a look at them. No, sorry, I've got that the wrong way round. It's been a while. The y-axis is the number of days, 1 to 6, 1 to 5. What have I got there? 1 to 7 there. So we've got 1 to 7 days, and the x-axis, that is time. So that goes from 6 a.m. to 6 a.m. the next day. Okay, so so this would be day 1, day 2, day 3, and this would be, and what you're seeing here in black is when the child is asleep. So this particular child would have a nap in the morning, a nap in early afternoon, and then they'll sleep throughout the whole night. So it's a pretty easy child. Okay, so that was the 9-month-olds. So let's have a look at the descriptive data. So here we see 9-month-old typically developing child, and again it's the same what we saw earlier, so a nap in the morning, a nap in the afternoon, asleep throughout the whole night. A bit unusual, but you get that sometimes. And then in Williams syndrome, the 9-month-old with Williams syndrome, see a huge difference. So I wouldn't even know how to describe this. There's a kind of a nap in the morning-ish, but it's a bit hard to see. So you can see it's very fragmented. Now as you get older, sleep should get better. So let's have a look at 14 months of age. So this is a typically developing 14-month-old, and the child is clearly having a nap in the afternoon and they're sleeping through the night. And then in Williams syndrome, again, it's very fragmented even at 14 months of age. At 24 months of age, you have this it's a typically developing child, and again, it's very, very regular. Okay, on one of the days, they're clearly not having their midday nap, but on most days, it's pretty regular. And then in Williams syndrome, it's extremely fragmented, so it's very difficult to predict what's going to happen on any particular day. At 26 months of age, so again, you'd expect sleep to be a bit better, but here's a typically developing child sleeping throughout the night. Kind of sometimes they have a nap, sometimes they don't. But in the Williams syndrome, 26-month-old child, again, it's a little bit more unpredictable. At 30 months of age, this typically developing child is annoying my data because they're waking up a lot at night time. But it's, at least they're napping in the afternoon. With Williams syndrome, again, it's a lot worse at 30 months of age. So what you can see is, that in Williams syndrome, there seems to be disrupted sleep compared to typically developing children. In Down syndrome, we see pretty much the same thing, perhaps even worse. So what we're seeing here is different children, and it looks even worse in Down syndrome. So if anything, their sleep looks even more fragmented than it does, just by visual inspection anyway. In Fragile X syndrome, we see something interesting. Sometimes it's very regular. So this child is awake or asleep. So they're sleeping throughout the night. So you see some really nice regular patterns here. And then sometimes you see completely irregular patterns. So you see something like this. So you're getting a lot of variability in sleep with Fragile X syndrome. So it's something quite interesting. Who knows, maybe there are different subgroups. So just to show you the results of this study, you have the children, the typically developing children are sleeping for longer. They're spending less time awake during bedtime. So the children with neurodevelopmental disorders are awake longer at night time. And then sleep efficiency, which is obviously kind of based on these measures, just shows that the typically developing children are getting a good night's sleep, whereas those with neurodevelopmental disorders are not. Okay, so what we found essentially is that sleep was disrupted in these groups, and that to the extent the typically developing children were getting an extra half an hour sleep each night. And it was also related to language development. So if you're a child with Down syndrome and Williams syndrome, you would understand an extra word for every additional 10 minutes of sleep you would get. So sleep was related to language. Okay, so just to summarise that, what we're seeing is attentional disengagement was associated with language development. Social orienting, neurophysiological social orienting response was associated with language development in Fragile X syndrome. And there's disrupted sleep with language was associated with language development in Down syndrome and Williams syndrome. We didn't analyse Fragile X syndrome because we didn't have a large enough number. Okay, so the next question is, though, does this predict later developmental outcomes? So what we're doing is we're now measuring sleep pattern. We're now measuring them now that they're 9-10 years of age. So we're using the British ability scales, LITER 3, early child attention battery, some iPad tasks that measure mainly attention, and the BPVS, which is language. And we're seeing whether these correlate. This is ongoing, so I don't have any results for you yet. But just to show you some analyses, so just be wary, this is just preliminary, just to show you some analyses. Just to remind you, there was a relationship between disengaging attention and language. So I just want to show you whether that corresponds to language. So this is infants and toddlers. Does that predict language around 9-10 years of age? So what I did essentially was, So what we had to do is there was a bit of a challenge with these analyses. So how do you relate early visual attention to language when the children are all slightly different ages? So what I did was I calculated the gap effect, calculated the contribution of age, and then I calculated the gap effect minus the contribution of age, so looking at the residuals. So basically I'm analysing the residuals. I just rushed through this, but if you want to know in more detail, I can tell you in a Q&A session, or I can tell you afterwards. But I'm just analysing the residuals just to kind of get rid of the age effect, because you're going to have children are being tested at slightly different ages, but age is an important factor, and we wanted to account for that. But accounting for that, what we see is we do see some patterns. So it seems like just with a few children we've already tested in Williams syndrome, it seems that there's a better attentional disengagement in infancy relative to age. So the better language comprehension we see at school age. So it does seem to be a long-term relationship. Okay, so I hope that was clear. If not, then you can see me afterwards. Okay, so moving on to external constraints. So far what we've talked about kind of internal constraints, and I think this is often how we think of children with neurodevelopmental disorders. So we do all these measures in the lab and so on, but of course there's lots of external constraints as well. I'll tell you one of them from Hannah D'Souza's lab, and Hannah's given a talk later today. So Hannah was looking at parental depression on language development. And what she found was that if you're just looking at parents who have never reported having depression at any point, then what you would see is what you would expect, which is something like this, and you would see that as the older the child, the better their expressive vocabulary score. And so this is kind of what you'd see everywhere. It's just what you'd expect. So the older the child is, the greater their expressive language. The interesting thing is, if either one of the two parents reported having depression at some point, and it doesn't need to be at a critical point, but at some point they reported having depression, what you see is that the language development was developing at a much slower rate than otherwise. So that's a quite powerful effect. So basically what this is saying is that even if just one parent has depression at one age in time, that could be a factor in the child's language development. So this just shows you the full range of all the factors we need to consider when we're thinking about individual differences. You've got everything from genetics all the way to society and onwards. So I just want to, so you could argue that depression, maybe that's a really powerful force, and so maybe it's not so surprising, I'm not sure. So I'm going to show you some preliminary data that's even more subtle. So it's, and this would need to be confirmed, so I'm not sure whether this will hold up with more studies. But some of you might be very familiar with the idea of the bilingual advantage. So this is the idea that there have been loads of studies over the last 20 or so years where bilinguals outperform monolinguals on non-verbal tasks of cognitive control. It's very controversial. There's a huge debate over whether it's a real effect or not. But what we wanted to do is we wanted to just see, okay, could it happen? Could it happen early in infancy, and if so, how? And the problem with the field is that there's no theory, or at least the theories will never be able to explain how these young infants develop it. So we thought, could we come up with something? Could we think about a way? So we've already seen that attentional disengagement may constrain language development. So what we wanted to do was to see whether that can happen the other way. So could being exposed to different language environments, could that constrain attentional development? So we're kind of trying to flip it and see whether it's a two-way process. So how would this happen? I mean, this is what nobody tells you in the bilingual advantage literature. There's just, the theories are pretty vague. So how would this happen? And when we started this, we didn't know, but what we did was Hannah and I brainstormed and we came up with a possibility. So the idea is that biological systems, all biological systems, including human infants of course, adapt to their environment by modelling the ever-changing world and anticipating events within it. So this is what all biological creatures do. And we do this by sampling information from the environment. And we sample information, by sampling, we're selecting information, we're acting on the external environment. And so these are the things we're doing on the external world, or interacting with the external world. And this results in different sensory input. And then we match the sensory input with the internal models that we're building up of our external environment. And if there's a mismatch between what we're sensing and what our internal model, then we can do one of two things. We can either change our internal model, or we need to get more information maybe. So we need to explore more. So this is a basic biological process. So bilingual infants, they receive fewer samples from each language than monolinguals do. And some of these samples are going to be more varied. So for example, one study in I think the Basque country, I forget now, but one study found that there are more, or Catalan actually, sorry, one study found that there are more pronunciation errors in bilingual homes compared to monolingual homes. So you're going to get more variability as well as fewer samples. So what effect would this lead to? Well, because we know that bilingual infants, they learn all their languages as fast as monolingual infants do, so they're not at any disadvantage, and in fact they're at an advantage because they end up knowing more languages. So how do they do this when their task is harder? So it could be that maybe they need to observe lip movements more, because obviously with lip movements, when you're observing lip movements, it helps disambiguate information. And so you often see, for example, that infants, they start out when they're very, very young looking at the eyes, but when they get to this crucial age, when they're starting to learn language, they start to look more and more at the mouth, and maybe that's a result of them learning and using lip movements to help them learn words. So what we argued is that it's possible that as you're getting a bit older and you're starting to develop the ability to explore more, you're playing with toys, there's going to be competition between, for example, the toys you're playing with and maybe someone speaking. And so you're going to have to drive your attention. You're going to have to shift your attention if you want to catch those lip movements as the person is speaking. And so maybe this drives the attentional system. So maybe you're being forced to look more frequently. Maybe with a monolingual child, you're just probably less likely to do so because there's just one language that you're learning anyway, and so you can just focus on your toy. So maybe this competition is driving the attentional process. So that was the hypothesis. So what we did was we used the gap overlap task that I described previously, but this time with a different group. We were looking at bilinguals. infants being raised in monolingual homes versus infants being raised in bilingual homes. So we're using the same task, and what you would expect is, if this hypothesis is true, then you would expect the infants from the bilingual homes, they should be able to disengage their attention and shift it, because that's what they're going to be doing between 7 and 9 months of age when they're developing, and they have that ability in this toy. So that's what the hypothesis. That's what the hypothesis was, and what we found was that is indeed what we found. So the infants from the bilingual homes were faster at disengaging their attention. And this is a very large sample. So this is 102 children. And so we found that they were faster at disengaging. And what we found was that the vast majority, 84% of the bilingual infants, so 85% of the bilingual infants were faster than the mean of the monolingual infants. So it's a really large, Cohen's d was essentially 1, so 0.99. So it's a really large effect, and you can kind of see it's the mean is between, I think, 60 milliseconds up to roughly 100 and something. So you can see it is a really large effect. Okay, so that was quite interesting, because we made that hypothesis. It was a pre-registered report, so we had no idea whether what was going to happen. But the more interesting thing would be, okay, so what would happen if you just showed them stimuli? So the idea is, does this ability to disengage attention and shift attention faster, does this lend itself into some kind of bias to explore more frequently? If you're naturally a child who's disengaging and shifting attention to see a speaker or maybe a bystander start speaking and you shift attention, is this going to bias the system to explore more generally? And that would be even more interesting. And so what we did was, this time we wanted to see whether this was internally driven. So it's not just something appears and the child externally just sees that appear and shifts. We want to know whether the child would do this, is internally motivated to do this. So we just showed them 2 stimuli on the screen, and to keep it interesting, one of the stimuli would gradually change over time. But essentially there are 2 stimuli on the screen. And what we found was that the bilingual children were indeed shifting their attention between the 2 stimuli more than the monolingual children. So this is really interesting, because it seems to suggest that something that may have initially started out as being externally driven, so there's something happens in the external environment and they're orienting towards it because it's important for them to do so, seems to be internalized in a way where even if you just put 2 stimuli there, they're more likely to shift their attention more frequently. And so that naturally leads you to ask, well, are the 2 correlated? And they are correlated, but only in the bilingual infants, which is again what you'd expect. So in the bilingual infants, those who are faster at disengaging attention were also the ones who were more likely to switch between the 2 stimuli more frequently. And this wasn't true there was no relationship in the monolingual infants. So this is quite exciting. Obviously this needs to be replicated. This is just one study, even though it was a large sample size, but it's only one study. But this kind of leads you to think about things such as, what kind of results might this lead to? So for example, is there a trade-off between exploration and exploitation? If you're someone who's always exploring at the expense of exploiting information, are you going to see these trade-offs? Also, there's this idea of plasticity. If you're open to exploration and experiences and so on, then you've got to retain plasticity for a longer period versus specialising to a very particular environment. And then obviously there's this idea, as we were talking about, the model between sensory evidence and prior expectations. So you have a model in your head of what you expect the world to be, but if you're more flexible, more plastic, then maybe in a more volatile world you're going to put more weight, or the brain will place more weight on sensory evidence or on sensory information versus your internal model. So you can imagine how you can start to have these individual differences based on the environment that you're growing up in. So this was a slight diversion, but I just wanted to kind of emphasize, to show that something even maybe subtle in the environment may play a role in infant development, including individual differences. But this wasn't done with neurodevelopmental disorders. Okay, so we wanted to know whether this has any predictive power, and indeed, actually, we ran this study on adults, and we just asked them, when did you learn your second language? And those who learnt their second language simultaneously, so in other words, they were born into a bilingual home, they were disengaging faster than those who learnt their second language much later on. So again, it kind of fits in with the evidence. Okay, so we just wanted to look into this in a little bit more detail, just to see what exactly was happening. So what we did was we came up with this program where we can look at our data, visualize our data more easily. And if you just focus on so what we're doing here is we're just looking at one trial. Okay, so this is the first trial, and the first trial, there are two things on the screen, and we're just looking at that first trial, and we're just looking at how many children were looking at the first stimulus they saw. So if you've got two stimuli, and let's say the child looks at the one on the left. We wanted to know, we were just saying how many, we just wanted to know where they were looking after that, if that makes sense. Does that make sense? Yeah, okay, so nods. Okay, so if we just look at the second figure below, this is just showing looking time for both groups. So if I think the blue was the monolingual. Blue's monolingual. I think you can see it better than me. It is? Okay. Okay, so blue's monolingual. And essentially what you can see is that they're both looking at both stimuli roughly the same time. So it starts off at 0 because obviously they should be looking at the center of the screen. There's always one child who's looking away, but most of the time it starts off at 0 and then it gets to, I don't know, 300 milliseconds, and then as more and more children have shifted their attention to one of the stimuli, it builds up until they're all looking at the first stimulus. So that's just looking time. But so we can ignore what happens in the first, say, 300 milliseconds. All of that would just be noise because they should be looking at the center, and most of them are. Almost all of them are. But the key interesting thing is what happens after that half second. So they by definition, they should all be looking at whichever stimulus they first land a look on. Okay, but that's how we're doing it by definition. So they're all looking at one stimulus, and let's just focus on the monolinguals for now, which is the blue line. So what happens is they're all looking at one stimulus, and then they gradually start to look, as a group, they start to look at the other side. So you look at one, you build up your representation of what that looks like, and then you want to see what the other thing is looking like. So you shift your attention to the other side, and then you start to build up that model, and then you shift your attention to the other side, build up that model, and eventually it starts to level out because you get these individual differences in this. They're flicking their looks at different times, so it starts to level out. So this is a classic textbook, what you would imagine happens. So nothing surprising here. These are the monolingual infants, exactly what you would expect, no surprises. So now let's look at the bilingual infants. Again, it starts off exactly the same by definition, that would have to happen, but almost immediately it's kind of 50-50. So what this suggests is that some are like darting back to the second one, darting back to the first one, second and first one, and on balance it's just 50-50, and so it's kind of a very unusual profile you'll see later on. If we jump now to the very last and final trial, in this trial one of the stimuli has changed, and it was changing gradually, getting more and more different. So by now the children would be more interested in the stimulus that is changing, and they would know which side that should be. So what you can see here is that both children obviously are looking at one of the stimuli, and the monolingual children are kind of staying at that new one. They're not switching to the other one, whereas the bilingual children are switching to the other side. So anything below that 50% line, they're looking at the other side. So what this tells you is that either the bilingual children haven't noticed that the two stimuli are different, which is very unlikely, or they're just naturally exploring, even when they know that there's nothing new, the stimulus is not changing, they're still naturally exploring and checking. And so I think it's a really interesting, because it's such a subtle effect, but you can kind of see these really interesting patterns. And I think I just wanted to include this because I just wanted to kind of show how important this could be. And I won't dwell on this, but because it's not about neurodevelopmental disorders, but just to kind of tell you, we also ran this study with adults, and we asked them when they learnt their language, and what we found was that adults who were more simultaneous bilinguals, so they learnt their second language very early, they were looking more at the novel stimulus. So there is evidence that the bilingual infants probably did know that the two are different, but they're just exploring anyway, which I find fascinating. So just to kind of wrap up, it's really important, obviously, to look across all these different levels and across developmental time. What you can see is maybe, for example, the words you hear in your environment may have a subtle effect on attention, on your looking behaviour, and then this might have, and then you've got your looking behaviour obviously constrains what you're exploring. And how you explore your environment constrains what you learn. How your looking behaviour will also affect how you interact with your parents or with others, and and again how you learn. Hannah might touch upon. I'm not sure how you learn words, for example, could be through how you interact with your parents. There's a lot of evidence for that, Linda Smith, etc. And then you've got things like, in Down syndrome, very poor vision and muscle tone. How does that affect things? And then we know that attention seems to correlate with language development. And then we know that either of the parent, either the mother or the father, has reported depression, that seems to affect language. And we see sleep seems to affect language via mood. And we haven't even spoken about things like synaptic plasticity, which we also know is awry in a lot of neurodevelopmental disorders. So you have this huge complex story. And we also haven't even spoken about how the child is adapting to these developmental constraints, which I think is a really important factor. So just to throw it out there, if you are interested in this even more important aspect, which I think we've barely scratched the surface of, we just got a book chapter out, Hannah and I, which goes into more detail and gives some examples of how a child with Down syndrome might adapt to different developmental constraints. And there's an older paper there if you're more interested in more general. So just to summarise, understanding early emerging abilities and their development, I think, is crucial, which is why I think this workshop is so important, and I'm looking forward to hearing all the other talks, because we cannot assume that what we know about adults applies to infants. Development is, of course, context and path dependent, so genes don't operate in isolation. There's just layers and layers and layers of context, and there's so many interactions that are happening, and of course this happens over time, and something that happens early might affect how the system responds later on. And we also showed, for example, how early language development seems to be constrained by visual attention, auditory attention, sleep, and from Hannah's lab, maternal depression. There's still a lot we don't know, so how do they emerge? What are these cascading effects? Some factors, are they protective factors? How does a child adapt to these? The plasticity, can we change the course of development, and so on? And what factors are most important? Because it's not like all the factors are going to be equal all of the time. Some might be more important than others, and that might depend on their developmental trajectory. Okay, so huge thanks to all the collaborators, everyone I've worked with on these projects, and all the families, participants, and funders. Okay, thank you.